In this recording, we are going to be discussing related rates for AP Calculus, what they are, what the problems look like, and some equations that you need to, have memorized in order to complete these problems. So, first of all, what are related rates? Well, in calculus, related rates problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. All right, most of the time it's with respect to time. So we're going to have some sort of related rate that has, when we take the derivative, has some, dr over dt or dA over dt, because everything is related to time. So that's what our denominator statement would be. Remember that rate of change refers to a derivative function, so therefore we will be taking the derivative of equations related to the problem. Depending on the problem, the equation will change. We are going to be using our implicit differentiation methods in order to take the derivative of these equations, because there are going to be more than one variable in these equations, so that's why we need our implicit differentiation. Once we have our derivative function, we will plug in the information that we do know and solve for the information that is being asked for. Now, some things that are very important key phrases to keep in mind is generally the word fast. How fast is something changing? And the rate at which something increases or decreases. These are generally the keywords that pop out during these problems. So if you see a problem that talks about how fast something is changing or the rate at which something increases or decreases, you are talking about a related rates problem, and therefore you should then know kind of where to go from there. So let's get started with some equations that we need to remember. So here are the main types of problems that you'll see, what they're related to. So we have circles. Now, the two equations that are most related to circles are the area equation, so A equals pi r squared, and circumference, so C equals pi d, or sometimes we can even think about that as C equals 2 pi r. Okay, so those are the two main equations that you need to be able to recall while we are for our related rates problems. For triangles, well, triangles we're dealing with the side lengths of the triangles. So since we're dealing with the side lengths, and for the most part we're dealing with right triangles, well, how do these side lengths of right triangles relate to one another? They relate to one another using the Pythagorean theorem. So a squared plus b squared equals c squared is our triangle formula that we need to know. For a sphere, we are then going to be talking about not area but volume, because we now have a three-dimensional figure. So area and circumference were needed for the circles because it was a two-dimensional figure. Now that we have a three-dimensional figure, we talk about volume. So volume of a sphere is 4/3 pi r cubed. For a cylinder, same thing. We are dealing with volume. That would be pi r squared h. For a cone, the cone formula, again, we are dealing with volume. That is pretty much the same thing as your cylinder. However, you have a 1/3 in front of it. But it's still a pi r squared h. So that cylinder and cone formula are pretty similar. The only thing that's different is that 1/3 in front of the cone. Think about it that the cone is a smaller amount than the cylinder. It's got part of it taken out. Well, how much of it is there? 1/3 of it. All right, and then angles, your trig functions. Most of the time, the trig functions that you will need are just your basic SOHCAHTOA functions. So sine of an angle equals the opposite over the hypotenuse. Cosine of an angle equals the adjacent over hypotenuse. And finally, tangent of an angle equals your opposite over adjacent. So those are the three main that we are going to be keeping at the forefront of our mind. Okay, so let's get into a problem. So from the packet that we were working on in class, If you go to example 5, which is technically on page 64 of that packet that we were talking about. We did example A in class, but now we're going to go over example B. So we have an oil tanker that spills oil that spreads in a circular pattern. So we have a circle, and let's go with, okay, so I've just got my circle on the center. That's where the oil spilled. That's my circular pattern, whose radius increases at a rate of 50 feet per minute. Now, once I see a unit measure that is not just feet, it is feet per minute, that means that I am dealing with a rate. They did also mention rate in the problem. But that means out of my given information, dr dt, the change in the radius over the change in time, is 50 feet per minute. So we're going to keep that off to the side. Now it says, how fast are both the circumference and the area of the spill increasing when the radius of the spill is, again, and we're going with part B. So my radius in this case is going to be 50 feet. All right, well, let's deal with the circumference first. So I'm trying to find how fast the circumference is increasing. So if I'm looking for how fast the circumference is increasing, again, that is a rate. So that would be dc dt. That's what I'm looking to find. So let's go through and take my circumference formula, which is c equals pi d. Now in this case, because all the other information that I'm given is as in the form of a radius, I'm actually going to use the 2 pi r formula rather than the pi d formula. If I had been given information about the diameter and how fast the diameter changed, I would use this first formula. But because the information that I was given was dr dt and r, that's why I'm going with the second formula here. So first thing we need to do is take the derivative. So the derivative of c would be 1 dc dt. 2 pi is just some coefficients. So when I take the derivative of r, that 2 pi will stay as a coefficient. And using the power rule here, 1 times 2 pi r is 2 pi r. This would become technically r to the 0 power, which reduces to 1. And then I have a dr dt, though, because I took the derivative of a radius. So now I'm going to plug in the information that I know. And the information that I know is that the rate at which my radius is increasing is 50 feet per minute. So that leaves me with just my unknown of dc dt. So I'm going to simplify this, and I end up with 100 pi feet. Now, some problems, if it was multiple choice, maybe this would be a calculator-based question that you'd have to evaluate that pi. But for our cases right now, we can leave it in terms of pi. But I do want some sort of units. Now, circumference is a distance around. So that means it would just be feet per minute. All right, if I was talking about area, it would be feet squared. If I was talking about volume, it would be feet cubed. But since circumference is simply just a distance, we leave it as feet per minute. All right, now going over to the area, I want to find how fast, again, the area is increasing. So in that case, that would be dA dt. How fast is that area increasing? Well, my area of a circle is pi r squared. That's my formula. So again, I need to take the derivative of that function if I'm looking for dA dt, that rate. dA dt is not currently in my formula here for area of a circle, so I need to do something to that formula in order to get dA dt. And what do? Take the derivative. So the derivative of A is dA dt equal to, using my power rule, 2 times pi is 2 pi. That would leave me with r to the first power, and because I took the derivative of r, I have a dr dt there. Again, let's plug in what we know. So I have 2 pi. The radius that I'm dealing with at this point in our part B was 50. And my dr dt was also 50. So if I go through and make that calculation, 50 times 50 is 2,500, times 2 is 5,000 pi. And now that we are dealing with a change in area, this would be feet squared per minute for my units, because feet squared would be more appropriate for our area. Okay, and so that would be our problem. That's it. So moving on to the next one. Let's go over example 6b. So again, this was a question that we did in class. We did part A in class. So now we are going to do part B. So let's read through. A 13-foot ladder leans against a vertical wall. So I have my vertical wall here, and I have a 13-foot ladder. Okay, so let's just extend that down. Okay. If the lower end of the ladder is being pulled away at the rate of 2 feet per second, how fast is the top of the ladder coming down the wall at 5 feet above the ground? Okay, so again, we're doing part B here. So the bottom of the ladder is being pulled away from the wall at a rate of 2 feet per second. Now, I have a right triangle going on here, so I'm going to just label this X, Y, and because this is a hypotenuse, I'm going to label it C. Now, again, it's a rate at which the ladder is being pulled away from the wall. So that is going to be dx dt, the rate at which this distance here is changing. Now, since this distance is going to be increasing at length, my rate needs to be a positive number. Okay, and again, that's because the length is going to increase. So they tell me the rate is 2 feet per second, so we have a positive 2 feet per second. What else do they tell us? They want to know at the instant that when the ladder is coming down the wall at 5 feet above the ground. So right now, this ladder is 5 feet above the ground, so that's my y value. Okay, well, we have a right triangle, so again, how do the sides of a right triangle relate? Well, by the Pythagorean theorem. So I have x squared plus y squared equals my hypotenuse c squared. Well, as we did before, I'm going to have to take the derivative of this function. So the derivative of x squared is 2x dx dt. When we had done implicit differentiation before, everything was with respect to x. So I would get here in this place dx dx, which would simplify out to 1. So I didn't really need to make that statement, right? We could just leave that part blank. However, I can't do that now because everything is with relation to time. Dx dt does not simplify to 1 because the numerator and denominator are not the same exact term. So it's not going to simplify, so I need to make sure that I leave this statement in my derivative. Moving on, so derivative of y squared is 2y dy dt equal to 2c dc dt. Okay, so let's talk about the information that I know. So right now for my x variable, okay, I don't know what x is, but I know that the rate dx dt is 2. Okay, plus, let's talk about my y variable. I know that my y is 5, but I don't know what dy dt is. Right? I don't know the rate at which that, I don't know the rate at which the top of the ladder is going down. And then separately, I know that my hypotenuse, the ladder length, is 13. I do in fact know what dc dt is. dc dt represents the change in the length of the ladder. Well, my ladder is not changing, okay? The length of that ladder is not changing. Therefore, the change in the length of the ladder would be 0. That length is not changing. The ladder is 13 feet, period. It's not changing, so dc dt would be 0. Now, let's go back and figure out what I'm trying to solve for. I want to find in this problem how fast the top of the ladder is coming down the wall. Well, that would be the change then in this height here, which is my dy dt. So this is my goal. I want to solve for dy dt in the problem. In order to do that, I need to know what my x value is. So how do we figure out the x value here? Well, I'm going to use my Pythagorean theorem. So I have x squared plus y squared equals c squared. And my x value is what I'm solving for. My y value is 5. And my c value is 13. So I have x squared plus 25 equal to 169. Subtract over that 25, so I get 144. And square root both sides, so I get an x value of 12. So if you were able to recognize this, all right, a 5, 12, 13 right triangle is one of your Pythagorean triples. Just like a 3, 4, 5 right triangle. So since my hypotenuse was 13, the two legs of the right triangle would have to be 5 and 12. If you didn't remember that off the top of your head, no problem. We have the Pythagorean theorem to help us. So this right here, I now found was 12. So we're going to go through and just multiply out. So 2 times 12 times 2 would be 48 plus 10 dy dt equal to 0. So let's subtract over the 48. 10 dy dt equals negative 48. And if I divide both sides by 10, I end up with dy dt equals negative 48 over 10, which could reduce to negative 24 over 5, or which could even as a decimal be written as negative 4.8. Now our units in this case, because it is a change in a distance, would be just feet per second. So any one of those three options would be an acceptable answer. But again, if this was a multiple choice question, it would all be dependent on what the multiple choice option was. Moving on to our next problem. So question number 9, which shows up on page 66 of the packet that we were working on. We have sand is poured on the beach, creating a cone whose radius is always equal to twice its height. So let me just draw a quick picture. We have a cone whose radius is always equal to twice its height. If the sand is poured at a rate of, so I have a rate here, so that's going to be some d over dt, of 20 inches cubed per second. Well, inches cubed right there tells me that I'm dealing with a volume. And because it's a rate of a volume, I have dv dt is 20 inches cubed per second. Those units are extremely important to us in being successful in these problems. Because just based on the units, I can tell whether I am dealing with a rate based on distance, area, or volume. So seeing that inches cubed, that means it's a volume, so I have a rate of a volume. So we have to be very careful to pay attention to those units. I want to know how fast is the height changing at the time the height is 6 inches. We're doing part B because we did part A in class. So how fast is the height changing at the time the height is 6 inches? So if the height is 6 inches, and I want to know how fast the height is changing. Well, that would be dh dt is what I'm looking to find. Okay, let's go to our volume of a cone formula. Now, we are never going to be taking the derivative in a related rates problem of a function that has two variables on either side. I want to find something that is not changing, and I'm going to replace that variable with something that I know about it. Okay, what do I mean? So I want to either replace R with something related to H, or I want to replace H with something that has to do with R. Well, let's think about the problem and what information I'm given, and more specifically, what I'm looking to find. I am looking to find dh dt. So looking ahead, if I were to take the derivative of this formula, I need there to be a dh dt in that function. which means I need to keep this h variable in the original function, which leads me to believe then that I am going to be replacing out r squared. Well, what does, and more specifically r, what do I know about r? The only thing that I know about r is that r is equal to 2h. Well, this is very fortunate for us because the information that they gave us about r was related to my height. So instead of having r that's being squared, I'm going to square what r is equivalent to, which is 2h. So now I have a volume function that is completely made up of, or I should say completely dependent on my height. So let's go. I have 4/3 pi h cubed. That is my volume formula of a cone that is solely based on height and where the radius is equal to 2 times the height, as they gave us in this problem. Okay, so I cannot use this volume formula every time I have a cone. This volume formula is simply specific to this problem, where the radius is always equal to twice its height. But now I can take the derivative of this function because it's completely within one variable on the right-hand side. So using the power rule, because 4/3 pi is my coefficient, 3 times 4/3 pi is going to be 4 pi h squared dh dt. There is the dh dt that I'm looking to find. So let's plug in what I know. Well, dv dt was 20. 4 pi, my h right now is 6. And I'm looking to solve dh dt. So 20 is equal to 36 times 4 is going to be 144 pi dh dt. And now I'm going to simply divide over that 144 pi. So I have 20 over 144 pi. My units for this, because it's the change in height, that is just a distance. So I'm going to simply have inches per second. Okay, and we can just leave that there for our purposes for right now. So in this case, in our cone formula, when I have both an r and an h, I'm going to be replacing one with respect to the other. So in this case, because I needed to get a function that was all based on one variable on the right-hand side, namely our h, because that's what I was looking to find, I needed to replace r with something having to do with h. Well, they very kindly told us that r is equal to 2h, so that's what I could replace r with. It's kind of like a substitution that we have going on here. Okay. And finally, the last problem that we're going to deal with is question number 6. Question number 6 shows up on page 68 in the packet that we were working on during class. We are again going to be doing part B, because again we did part A in class. So we have a 12-foot ladder that stands against a vertical wall. So I have a wall with a 12-foot ladder. So this is 12. If the lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second, how fast is the angle of elevation of the ladder changing at the same instant? Ooh, okay, so I'm going to label this X, I'm going to label this Y, and I'm going to label this C. So in this case, again, I have the ladder being pulled away. So my rate here, my dx dt, is again 2, and it is positive again because X is going to increase in length. So since X is increasing in length, my rate is positive. So the lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. How fast is the angle of elevation of the ladder changing? Well, the angle of elevation of the ladder is right here. That's your angle of elevation of the ladder. So let's label that theta. So right now, let's look at the information that I am given. I'm given something about the adjacent side to my angle, and I know something about the hypotenuse to that angle. Well, that leads me to believe that I am going to be using a cosine function here, because that would be using your adjacent and your hypotenuse in order to help us find that angle. Well, let's look at what we have, which is not too much right now. My adjacent side is a length of x, and my hypotenuse side is a length of 12. Well, with that, we have to take the derivative. Now, before I take the derivative, I'm just going to rewrite this a little bit. I'm going to rewrite this as 1/12 x. That way that I can treat this, when I take the derivative, I can treat this as a power rule rather than having to go through the entire quotient rule. So let's take the derivative. The derivative of cosine is negative sine. And because I took the derivative of the theta, I now need d theta dt. That's right, your rate of change goes along with angle measures as well as x's and y's and any other variable you could think of. Now, if I take the derivative of the right-hand side, well, I have x to the first power, so 1 times 1/12 is 1/12. X would go to x to the 0 power, which is 1, but I need an dx dt there while I go through this. So let's think about what else we know. Now, something that it says in the problem is, how fast is the angle of elevation of the ladder changing at the same instant? Meaning, the same instant as part A. Well, let's look back at what was happening in part A. In part A, how fast is the ladder coming down the wall at the instant it is 6 feet above the ground? So I want that same instant in part B. So that means I have 6 feet above the ground is where that ladder is. So that means that I actually do know my opposite side of this triangle as well, which is going to be very helpful for us, because right now I need to start plugging in for things that I know. So let's look at what I know. I know right now that this is 1/12. I know that my dx dt is 2. I do not know what my d theta dt is. That is actually what I'm looking to find. How fast is the angle of elevation changing? That would be my d theta, my rate of change of the angle. Now my sine theta, well, again, here's my angle measure over here. Sine of some angle is the opposite side over the hypotenuse. Well, what's the length of the side opposite theta? Well, that's over here, your 6. And what is the length of the hypotenuse? That's over here, 12. So I actually can replace sine theta with the opposite of that angle measure divided by the hypotenuse of that angle measure, which is 6/12. We cannot forget about that negative sign, though, that was in front of sine. So this could reduce to negative 1/2 d theta dt set equal to 2/12 would be 1/6. And now I'm going to go through and I'm going to multiply both sides by -2, which is the reciprocal of that negative 1/2 in front of the d theta. So that will get d theta by itself. So I have -2/6, which is -1/3. And in AP Calc, I need my units. Theta, the angle measure that we always deal with in calculus, is radian measure. So I have -1/3 radians per second, not degrees per second, radians per second, because this is a change in an angle, so I need either radians or degrees. Well, in calc, we go according to radians. So -1/3 radians per second is how fast that angle is changing. All right, well, hopefully this has been helpful, kind of going through different examples, and please make sure that you continue working on some other examples and going over questions from that packet for review. Okay?